We have some root locus examples here. Let us say sketch the root locus for a unity feedback system with an open loop transfer function g of s is equal to k upon s into s square plus 4. So we have discussed a set of rules for the construction of the root locus. So step 1, the number of open loop poles are 3, therefore the number of branches in the root locus are 3. The 3 branches of the root locus originate from open loop poles s is equal to plus minus 2j and 0 when k is equal to 0, and all the 3 branches terminate at infinity when k is equal to infinity. All test points on the real axis between 0 and minus infinity have an odd number of poles to the right hand side. Therefore, all poles between 0 and minus infinity are a part of the root locus. So if we really draw the root locus, can you see that there is a pole at s is equal to 0, pole at plus 2j and pole at minus 2j. Now, the 3 root loci that proceed to infinity do so along asymptotes. Phi a is equal to 2q plus 1 into 180 degrees by n minus m. So what is n minus m? 3. So what do you have? 2q plus 1 into 180 degrees by 3. So if you put q is equal to 0, you are going to get phi a is equal to 60 degrees, and if you put q is equal to 1, you are going to get 180 degrees, and if you put 2, you are going to get 300 degrees. The centroid, the point of intersection of the asymptotes on the real axis, is given by sum of real parts of the poles minus sum of real parts of the zeros divided by number of poles minus number of zeros. So sigma a is equal to 0 minus 0 by 2, which is at 0. So which means the centroid is now at 0. If you can see the diagram, the dotted white lines are showing the asymptotes. So you have one asymptote at 60 degrees, the other one at 180 degrees, and the third one at 300 degrees. If you really see, there is one root locus branch which is going from 0 to minus infinity, and there are 2 branches which are going along the asymptotes. Take another example. G of s h of s is equal to k into s plus 1 divided by s plus 2 plus s plus 3 plus s plus 4. The open loop poles are at minus 2, minus 3 and minus 4, and open loop 0 is at s is equal to minus 1. Therefore, n is equal to 3 and m is equal to 1. The number of branches of the root locus are 3, so n is equal to 3. The 3 branches of the root locus originate from open loop poles at s is equal to minus 2, minus 3 and minus 4 when k is equal to 0. Since m is equal to 1, out of the 3 root locus branches, only one branch terminates at open loop 0 and the remaining 2 branches terminate at infinity. All points between 0 and minus 2, between minus 3 and minus 4 lie on the root locus, since the sum of poles and zeros to the right of these points is an odd number. The 2 root locus branches that proceed to infinity do so along asymptotes. Phi a is given by 2q plus 1 into 180 degrees by n minus m. So here q is 2. So q is n minus m is 2. So q is 0 and 1. If you take phi a at 2q plus 1 into 180 degrees by 2, you are going to get phi a as 90 degrees and 270 degrees. So which means the 2 branches which proceed to infinity do so along asymptotes 90 degrees and 270 degrees. Now let us see a picture of the pole and 0 pattern. The 0 is indicated by red and the poles are represented by green. As I increase the k of the system, the centroid, the point of intersection of the asymptotes, is given by sum of real parts of the poles minus sum of real parts of the zeros divided by number of poles minus number of zeros. So where are the poles now? At minus 2, minus 3 and minus 4. There is no imaginary part. So sigma a is equal to minus 2 into minus 3 into minus 4 minus of minus 1 divided by 3 minus 1. So this centroid is now at minus 4. The breakaway points are given by solution of dk by ds is equal to 0. So 1 plus k into s plus 1 by s plus 2 plus s plus 3 by s plus 4. So k is given by minus s plus 2 plus s plus 3 plus s plus 4 by s plus 1, which is given by minus of s cube plus 9s square plus 26s plus 24 by s plus 1. This is u by v form, so if I do a u dk by ds, I should get s plus 1 into 3s square plus 18s plus 26 minus s cube plus 9s square plus 26s plus 24 divided by s plus 1 whole square. If you really simplify this, you are going to get s cube plus 6s square plus 9s plus 1 is equal to 0. If you solve for this, you are going to get 3 roots, 3.5321 minus 2.3473 and minus 0.1206. The root minus 3.5321 alone lies on the root locus, hence the breakaway point is at minus 3.5321. The complete root locus plot is as shown. So if you can see, there are 3 branches and one terminates at a 0, the other 2 terminate at infinity. And they do so along asymptotes which are 90 degrees and 270 degrees. Take another example. GFS HFS is equal to k into s plus 1 by s square plus 4s plus 13. The open loop poles are at minus 2 plus minus 3j and the open loop 0 is at minus 1. That is, n is equal to 2 and m is equal to 1. The 2 root locus branches, since the system has 2 open loop poles, there are 2 root locus branches. So this is the organization of the pole 0 pair. As you see, the 2 branches of the root locus start at open loop poles minus 2 plus minus j3. One branch terminates at open loop 0 since it has only 1 0, and the other terminates at infinity when k is equal to infinity. All the points on the real axis between minus infinity and minus 1 are on the root locus branch. The root locus branch that terminates at infinity do so along asymptotes phi a is equal to 2q plus 1 into 180 degrees by n minus m. What is n minus m in this case? 1. So what you have is, you have only one asymptote which is at 180 degrees. The breakaway points of the root locus is given by minus s square plus 4s plus 13 by s plus 1. If you do, this is a u by v form, if you do dk by ds, you get minus of s plus 1 into 2s plus 4 minus s square plus 4s plus 13 by s plus 1 whole square. If you really solve this, you get s square plus 2s minus 9 is equal to 0. The 2 roots are at s1 is equal to minus 4.16 and s2 is equal to 2.16. The breakaway point is at minus 4.16 since the point is on the root locus, but the other root 2.16 is not on the root locus. The angle of departure from an open loop pole is given by phi p is equal to plus minus 2q plus 1 into 180 degrees. For q is equal to 0, phi p is equal to plus minus 180 degrees plus phi, where phi is the net angle contribution at this pole due to the other open loop poles and zeros. Now let us consider the pole at minus 2 plus 3j. The net angle contribution is 108.43 minus 90, which is 18.43 degrees. This is shown in the figure as shown. So angle of departure of the pole is plus minus 180 degrees plus 18.43, which is plus 198.43 degrees. Similarly, the angle of departure of pole P2 is minus 198.43 degrees. The complete root locus plot is as shown in the figure. So we have 2 poles minus 2 plus j3 minus 2 minus j3 at 198.43 degrees. Let us take another example. Sketch the root locus plot of a feedback system where GFS HFS is given by k into s plus 2 by s plus 3. Using the rules, we can sketch the root locus. The open loop poles are at s is equal to 0, s is equal to minus 2 and minus 3. There is no open loop 0. So this is the location of the poles. If you see, at s is equal to 0, s is equal to minus 2 and s is equal to minus 3. The number of root locus branches is 3 since the number of open loop poles is 3. The 3 branches of the root locus originate from the open loop poles at s is equal to 0, minus 2 and minus 3 when k is equal to 0, and all the 3 branches terminate at infinity when k is equal to infinity. All the points on the real axis between 0 and minus 2, between minus 3 and minus infinity lie on the root locus, for which the number of open loop poles and zeros to the right of the test point are 1 and 3 respectively. The 3 root locus branches that proceed to infinity do so along asymptotes. Phi a is given by 2q plus 1 into 180 degrees by 3. Here n minus m is 3, so q is 0, 1 and 2. If you put q is equal to 0, 1 and 2 in the above equation, you get phi a is equal to 60 degrees, 180 degrees and 300 degrees respectively. The centroid, the point of intersection of the asymptotes with the real axis, is given by sigma a is equal to sum of the real parts of the poles minus sum of the real parts of the zeros divided by number of poles minus number of zeros. So you have 0, minus 2, minus 3, minus 0 by 3, which is equal to minus 5 by 3, which is minus 1.667. The breakaway points of the root locus are a solution of dk by ds is equal to 0. So gs hs is equal to k upon s into s plus 2 into s plus 3, 1 plus g of s h of s is equal to 0. So g of s h of s is equal to minus 1. Which particularly means that k s into s plus 2 into s plus 3 is equal to minus 1, or k is equal to minus s into s plus 2 into s plus 3, which is minus of s cube plus 5s square plus 6s. If you do a dk by ds is equal to 0, then you are going to get minus of 3s square plus 10s plus 6 equals to 0. So the roots of this are minus 2.5485 and minus 0.7847. The point minus 2.5485 is not on the root locus, therefore the breakaway point minus 0.7847 is on the root locus. So here you can see a centroid and the various poles which are marked. So if I want to find out the intersection of the root locus with the imaginary axis, this can be determined by Routh criteria. So 1 plus g of s h of s is equal to 0. 1 plus k s into s plus 2 plus s plus 3 should be 0. S into s plus 2 into s plus 3 plus k is equal to 0, which means s cube plus 5s square plus 6s plus k is equal to 0. If I draw the root thing, I have s cube, s square, s1 and s0. So taking the first row coefficients, you have 1 and 6 and you have 5 and k. If you solve for the third row, you are going to get 30 minus k by 5 is equal to 0, and the fourth row will come out to be k. Now for this system to be stable, k should be greater than 0 and 30 minus k should be greater than 0, which particularly means that the range of k for stability comes out to be 0 is less than k is less than 30. To find out the point at which the root locus intersects the imaginary axis, put k is equal to 30, so 5s square plus k is equal to 0, or 5s square plus 30 is equal to 0. So s square comes out to be plus minus j square root of 6, which means s square is equal to plus minus j 2.449. So if you really draw the root locus, what you can see is the root locus intersects the imaginary axis at plus j 2.449 and minus j 2.449. So this is the root locus. If you really see, this is the direction in which the closed loop poles will move. Take another example. Supposing I have k s into s plus 1, this is s plus 3. The number of root locus branches is 3 since the number of open loop poles is 3. 3 branches of the root locus originate from the open loop poles at s is equal to 0, s is equal to minus 1 and s is equal to minus 3, and k is equal to 0, and all the 3 branches terminate at k is equal to infinity. If you really see the root locus, means the pole open loop pole plot, you can see finally 3 poles. There is no pole at 0. All the points between 0 and minus 1 and between minus 3 and minus infinity lie on the root locus, for which the number of open loop poles and zeros to the right of the test point are 1 and 3 respectively. The 3 root locus branches that proceed to infinity do so along asymptotes with angles. Phi a is given by 2 cube plus 1 into 180 degrees by 3. So phi a is equal to 60 degrees, 180 degrees and 360 degrees. The centroid, the point of intersection of the asymptotes on the real axis, is given by sum of real parts of the poles minus sum of real parts of the zeros divided by number of poles minus number of zeros. So 0, minus 1, minus 3, minus 0 by 3, which is equal to minus 4 by 3. So this comes out to be at minus 1.33. The breakaway points, the root locus, are the solution of dk by ds is equal to 0. So g of s, h of s is k, s into s plus 1, s plus 3. So 1 plus g of s, h of s equals to 0 is k into minus s into s plus 1 into s plus 3, which is equal to dk